A rock of mass 2 kilograms is launched vertically upward with an initial speed of 60 meters per second from ground level, but this one experiences a drag force that is directly proportional to its speed and reaches a terminal velocity of 40 meters per second on its way down. So, as usual, we will start with the free body diagrams. We have one free body diagram for the way up, one at the highest point, and then one on the way down after reaching terminal velocity. So, all three of them have a downward gravitational force, and that force of gravity is the same, so I'll mark them with the little tick marks indicating they're all the same. And because there is air resistance present in this problem, we have to include the drag force. So probably the easiest one is on the way down after reaching terminal velocity. We know that the drag force is in the upward direction, and since it's at terminal velocity, the forces are balanced, so that drag force is equal to the gravitational force. At the highest point in the motion, the middle diagram, we know that the velocity for this one is equal to 0, and we also know that the drag force is equal to the proportional to the velocity. So that means that the drag force will actually be 0 at the highest point. So at the highest point, you only have the gravitational force acting on it. And the first diagram, on the way up, you know the drag force always acts in the opposite direction. So there's actually going to be a drag force in the downward direction. So I'll draw a second downward arrow and label that one as the FD. Part B. Briefly explain what happens to the magnitude and direction of the net force on the rock from the moment it is released until just before it hits the ground. We know the net force is just the vector sum of all the forces. So on the way up, the vector sum of the forces, because these are pointing in the same direction, you would add them together. So we can say that the net force in the y direction is equal to Fg plus Fd on the way up. And because the Fd gets smaller as the rock goes up, because the rock is slowing down, that means the V is getting less, which means the Fd is getting less, we can say that the overall net force decreases. So I should put a downward arrow to represent that it's decreasing. But also the fact that the net force is in the downward direction. So I guess this downward arrow here represents the direction of the force and the fact that the net force is decreasing. So it decreases until it reaches the highest point, and at the highest point, that net force in the y direction is equal to just the gravitational force. So that is just at the top. So it's decreased down to that value, but then it continues to decrease even further on the way down, because on the way down, the net force in the y direction, and I hate how the y's keep looking like g's, the net force in the y direction is equal to, now on the way down, we're going to say, because they're in opposite directions, according to this diagram, if we make downward the positive direction, let's do be this force minus this force. So we can say that it is Fg minus Fd on the way down. It's still pointing in the downward direction overall because the Fg, the downward force of gravity, is bigger than the Fd, the drag force, up until it reaches terminal velocity. So on the way down, it's a downward pointing force that is decreasing until the terminal velocity, or the VT, is reached. Part C. Is the magnitude of the drag force on the rock equal to 0 at any points in the rock's motion? Well, we already said in this diagram right here that since the velocity is equal to 0, since V is equal to 0, and the drag force is equal to B times V, this means that the drag force would be equal to 0 for that split second of time, that instant in time, at the very top of the path. But everywhere else along the path, because the rock has some velocity to it, that means there is a drag force acting on it. Part D, the rock rises to its highest point in the time, which we're going to call T rise, and then it falls back to its lowest point in what we're going to call T fall. And you just want to compare those two times. Now, this may throw some people off because in class we had just talked about the fact that when there's no air resistance, that these two things will be equal to each other. The time it takes to go up is equal to the time it takes to go down. And that's because the net force is the same the whole time, because you only have the downward force of gravity acting on it and nothing else. So because the net force is the same, the acceleration is the same the whole time, which means the time it takes to go up is going to be equal to the time it takes to go down, because it decelerates, it slows down going up at the same rate that it speeds up coming down. But this time, they're not going to be the same. So we're going to figure out what symbol goes between them. And the way to think about it is that on the way up, you have the greatest possible net force because you add them together, but on the way down, you have a much lower net force overall because you're subtracting them. So the acceleration is going to be higher on the way up. So we say the acceleration, the A, is higher on the way up. And because the acceleration is higher, that means it's going to take less time, or a lower t value. So the time it takes to go up is going to be less than the time it takes to go down. On the time it takes to go down, because the two forces are pointing in opposite directions, leading to a low net force, that means there's going to be a low acceleration. At some point, it's going to be zero acceleration, so it does not go to the ground as fast as it goes up. And part E, calculate the drag constant for this rock in the surrounding air. With a drag constant, you determine in that last part right here when it's actually reached terminal velocity. So at terminal velocity, we're going to say that the net force in the y direction is equal to 0. So Fd is equal to Fg. Plugging the formulas in, Fd is b times v, Fg is m times g, and then just solving this to get the v by itself. V is equal to mg over, actually we're looking for b, so b is equal to mg over v. M is 2 and g is 10, so mg is 20. V is the terminal velocity, which is 40, so b is equal to 0.5. The units of b, in the top we have a force, that's units of newtons, and in the bottom we have a velocity, which is units of meters per second. If you break down the units of newtons into a kilogram meters per second squared, a bunch of stuff cancels out, and you just end up with units of kilograms per second.